Today's goal is to use the empirical rule to infer, again that means to draw conclusions about proportions, those are percentages or parts of the whole, of normally distributed populations. Notice that means that normally distributed is a requirement of today. We won't be able to use this rule, whatever it may be, about populations that are not normally distributed. So typically populations are so big, the idea again behind inference is that typically populations are so big that you can't collect data from every single member of the population. So we get data from a sample, and then again we're trying to infer or draw conclusions about the entire population just by using the information we have from that small group of people we surveyed or collected data on, just from that sample. Okay, take a look at example 1. Suppose the distribution below represents ACT scores of a random sample of juniors from Central High. If a student was selected at random from the sample, so from these students that we have their information from, what would you expect their score to be? Well, I can see that this data is approximately normally distributed. I'm going to draw that bell curve. Oops, I'm only cutting values off. I didn't have a lot of gap in between, so let me draw one more. Again, I'm cutting off some values, but I'm leaving some gaps in between. I'm trying to sort of split the difference between the two. It's approximately bell-shaped, approximately symmetric. The average would be maybe here-ish. So a typical student would score maybe a 22, a 23. If a randomly selected student from the sample scored a 19, would you be surprised? No, it's not exactly the typical score, but it's pretty close to typical, so that'd be like sort of normal, right? If they scored a 13, now very few students are scoring a 13 or below, so I might be sort of surprised. That's sort of an atypical score. So these are information from the sample. C is asking, what about the entire group of Central High juniors, right? Well, although we only have information from the sample, assuming that our sample is not biased, it's not like a convenient sample of only your group of friends or the first 100 people at the ACT that day or something like that. But assuming this is a random sample, we think the entire population looks pretty similar to the sample. So we would again say scores like 22, 23 would be average or very, very typical. Scores like 19 and maybe 26, 27. They're not average, but they're not totally uncommon. Whereas a score like a 36, a perfect score on the ACT, would be really surprising or unlikely. It's similarly, a score like an 11, a 12, a 13 would be pretty low. So these are sort of speaking in generic terms about typical and atypical values. But we can actually quantify how likely scores will be within a certain range using the empirical rule. So empirical means based on observation or evidence. So let's just break down this word so we understand why we would call it the empirical rule. So for example, I as a teacher have empirical evidence, I've observed and I've experienced that students who don't do much homework are unlikely to get high scores on exams, right? That's my empirical conclusion from many years of watching students. So what we've noticed or observed from normally distributed data is actually way more specific. We can conclude that in a normally distributed population, even if we only have information from the sample, we can conclude that 68% of the population values will fall within 1 standard deviation of the sample mean. And 95%, so virtually every member of your entire population, will fall within 2 standard deviations of your sample mean, and 99.7, so now truly almost every single member of your population will fall within 3 standard deviations of your mean. So let's apply this a little bit. So if you are a potato chip company, then you have machines that would fill your bags, but of course not every single chip is going to be exactly the same size, so there will be some variation in how heavy these bags are, right? So if you have a normally distributed curve, it's going to look like this. With our mean, this value is a Greek letter mu, M-U, and it's for population mean. So maybe we know the mean of the sample, maybe we know the mean of the entire population, right? Sample mean would be x bar. And standard deviation, this is the Greek letter sigma, It's the lowercase sigma. Uppercase sigma we learned in sequences and series. And this would be the population standard deviation. So maybe we have that information. I'm going to draw sort of a bar out to my inflection point. If sigma, my standard deviation, is 0.05 ounces, then we can label this sketch with values 1, 2, and 3 standard deviations away from the mean. So all we're doing is adding 0.05, or 500ths, and then I need this same sort of width to go out here. Well, this makes sense. Now I'm sort of on the outskirts of the data values because we know within 3 standard deviations, 1, 2, 3, you're including virtually every single value. And so this would be the number of ounces of a bag of chips. And now I'm just going to take that same value and sort of width and subtract it. Okay, so here's my curve. So now we can answer some questions about it. Even though we only have information from a sample, we can pretty confidently say 99.7, well, that's 3 standard deviations of the mean. Well, that would be 8.97 to 9.27 ounces, right? And so we're saying I can guarantee that absolutely almost every single bag of chips will weigh between 8.97 ounces and 9.27 ounces. This might be important if you're on customer control and people are mad because they said, oh, I bought a 9-ounce bag of chips and it was actually 8 ounces. In this case, you'd say probably not, because only 0.3% would be less than 8.97 ounces, so you probably didn't get a bag of chips that was actually 8 ounces. Okay, what proportion are between 9.07 ounces? That would be here. And 9.17 ounces, so that's 1 standard deviation below and 1 standard deviation above the mean. So 68% of the bags of chips weigh between 9.07 ounces and 9.17 ounces. And then finally, let's shade the curve. Oops. Sorry about that. Let's shade the curve that represents the proportion of data within 2 standard deviations. So 1, 2. I'm going to shade from here up to 1, 2. So I'm shading in between here. And then explain what our answer means in terms of the context of the problem. Well, this shows that 95% of the bags of chips weigh between 9.02 ounces and 9.22 ounces. Let's look at just one more example. The U.S. Mint checks the weight of newly minted nickels. Again, you're making a bunch of nickels. They should all be approximately the same weight, but there's going to be some amount of error. They won't be all an identical weight. So here's a random sample of 100 new nickels. The mean and standard deviation are 5 grams and 0.06 grams. So let's actually mark that on here so we can sort of catch a sense. You're saying this is the average. That makes sense. It's approximately in the middle. And the standard deviation will be 0.06. So this would be 1 standard deviation away from the mean, 2 standard deviations from the mean, and so on. Okay. Approximate the proportion of the data within 1 standard deviation of the mean. So that would be adding 0.06 to the mean and subtracting 0.06 from the mean. So that would be these 2 values. So approximate the proportion of the data. If it's within 1 standard deviation, we know that 68% of the newly minted or created nickels weigh between 4.94 and 5.06 ounces.